Good morning. I welcome you all to this session of fluid mechanics. Now, last class we were discussing about the different forms of energy that a fluid particle or a fluid mass possesses in course of a flow. That means when a fluid particle is flowing or a fluid mass is flowing, what are the different forms of energy if we recognize a mass of fluid flowing can it have? Number one is internal energy, which is because of its intermolecular energy, which is because of the kinetic energy and potential energy of the molecule, that any substance has an intermolecular energy at any temperature more than the absolute zero. So, therefore, intermolecular energy is the first, number one. Number two is the kinetic energy. Because of the velocity, any particle or any lump of fluid does have a kinetic energy, which is given by the mass times the velocity square by 2, mv square by 2. Then we know the potential energy. The definition of potential energy is the energy which a particle or a mass possesses by virtue of its position in a conservative force field. If we consider gravity as the only body force field, so this potential energy is the potential energy due to gravity, which can be expressed for a mass m as mg into h or z, whatever you call, where z or h is measured from an arbitrary datum where we take the potential energy to be 0. So, apart from these three usual terms of energy or three usual forms of energy, there is another form by which a fluid particle or fluid mass possesses energy in course of flow is known as the flow work. So, first better to recognize it in terms of the work, then I will come to the terminology of energy. Now, one has to know that a fluid particle to flow through a medium, it has to continuously push its neighboring downstream particle, otherwise you cannot go. Just consider in a queue, if you have to move, you have to continuously push your downstream particle or downstream neighbor so that you can make your way through. Similarly, the thing happens in a fluid flow. For example, if we recognize a layer of fluid in a flow, then we will always consider if this layer has to go or move in the flow, it has to push its neighboring downstream layer to make its way through. So, therefore, this way each and every layer does work on its downstream neighboring layer, and this work he is capable of doing because of some energy stored in it. That is the way the energy is stored in a fluid particle. Now, let us recognize it mathematically, that let us consider a pipe or duct through which the fluid is flowing. Let us consider a layer here at any instant where the pressure is P. Let us consider a small layer like this. Now, after a time t, exaggerated view, that is small time, this layer has moved through a distance, that means this layer AA has moved here through a distance dx. Because of the flow it has to move. So, this movement implies that at this position this layer pushed the neighboring layer which was adjacent to this layer downstream to this, has moved through a distance dx. So, therefore, the layer A has done some work on its neighboring downstream layer which has come here. Okay. Now, what is the force that is being exerted by this layer A to its downstream layer? This force is pressure times the cross sectional area, if you take the cross sectional area A. So, this is the force. So, work done is force times the displacement. So, displacement is dx in the same direction of force, that means P A dx. So, this is the work that is being done by any layer at a pressure P to its neighboring downstream layer to maintain its flow. So, if we express this work per unit mass of the fluid element, then we can think of P A dx divided by a fluid element which is being displaced, basically this dx into A. So, therefore, we can write this dx A into rho, so that this term cancels. So, this becomes P by rho, which is very important term. That means, the work done per unit mass of a fluid element for its flow at any section is given by the term P by rho. So, this P by rho is known as, so therefore, this P by rho is known as the flow work. That means, one layer has to do this work. This we conceive in terms of a energy in this way, that by virtue of some energy this layer is capable of doing work on its neighboring layer. So, therefore, this amount can be thought of as an energy inherently stored in this layer because of the existing pressure P. This is the only way one can think of P by rho as a form of energy, and little loose term we tell it as pressure energy. That means the energy which a layer possesses by virtue of its pressure at an existing section, because of which it has the capability of doing work on its neighboring layer to push its way through, is known as the pressure energy. This is the only definition probably you can have for pressure energy. You can have this definition rarely in any book, but in my book it is explicitly written that this is the only way you can define the pressure energy. So, therefore, we see in a flowing fluid, because of the existing pressure at any section, the energy per unit mass of a flowing fluid is P by rho. So, therefore, now we can recognize what are the different forms of energy that a fluid particular mass possesses. These are like this. If I denoted the energy per unit mass, we can write this is Ui, where Ui is the intermolecular energy per unit mass, plus the kinetic energy per unit mass, plus this pressure energy per unit mass, plus the potential energy per unit mass. So, these are the usual 4 forms of energy that a fluid particular mass possesses, which have been expressed in terms of per unit mass. This is intermolecular energy per unit mass, this is kinetic energy per unit mass, this is pressure energy per unit mass, and this is potential energy with only body force field as the gravitational force field, potential energy per unit mass. Now, if we recall back the energy equation applied to a control volume through the Reynolds transport theorem, then we can see that d dt, sometimes small d, capital D, does not matter, the substantial derivative for a system which you know is equal to the total energy interaction by the system with respect to surroundings, and thermodynamics tells that there are 2 forms by which the energy is interacted between a system and its surrounding, that is the external to the system, one in the form of heat, another in the form of work. And if we consider the positive senses of heat interaction or exchange as the heat supplied to a system and work done by a system, then this difference takes care of the net energy interaction, the energy coming in minus energy going out. So, net energy coming in, which is responsible for the change of energy for a system. So, this is precisely the statement of the conservation of energy for a system. This becomes equal to, in case applied to control volume with the help of Reynolds transport theorem, is the rate of change of, that you have already, energy for the control volume Cv, as you know. What is that? Eta. Now, eta is E here. So, we write now E, Ui plus V square. If you recall, this thing we wrote earlier, only E was written. Now, instead of E, now we replace, because now we have recognized the different forms of energy per unit mass possessed by the flowing particles. So, this times rho dV plus the net rate of efflux over the control surface. Similarly, this thing will come, this is E plus P by rho plus Gz, I think that is okay, times rho V dot dA. So, therefore, this is precisely the general energy equation. General energy equation. This is known as general energy equation. General energy equation. Good. In case of steady flow, this first term will be 0. That means del Q, del T minus del W, del T will be this one. So, this is the. So, afterwards, for any problem, we have to start from this general energy equation, and we will see what are the special forms under special situation. Now, though this is a general energy equation, sometimes we want a little simple convenient form of the energy equation, which is the energy equation along a streamline. What is energy equation along a streamline? So, this question comes, what is energy equation along a streamline? Along a streamline. Energy equation along a streamline. What is this? we want to derive the energy equation along a streamline, sometimes that is more simple and useful also. Let us consider along a streamline we derive the Euler's equation. Let the direction is s. Now, along a streamline means the velocity vector is only along this direction. So, we can write that velocity is a function of s, the displacement along this streamline, and the time. Similarly, the pressure is a function of s and t. These are the only two variables in a fluid flow. Fluid flow means flow of fluid for an inviscid fluid, ideal fluid. There is no shear stress, only pressure is the surface forces and velocity. So, velocity is a function of s and t, p as a function of s and t. And we derive the equation of what is that equation of motion, that is the Euler's equation this way, del v del t plus v del v del s is equal to minus 1 upon rho del p del s plus next term g dz ds. That means, if we have a velocity field described by s and t as a function of s and t, pressure as a function of s and t, they must satisfy this equation, which is the equation of motion along this streamline, and this equation is known as Euler's equation according to the scientist Euler who first deduced this. Now, we know from physical sense that the work done by the application of force is equal to the force times the displacement in the same direction, that means F dot ds. That means, if we multiply the force with the displacement in the same direction of force, then we can find out the work done by that force, and that is gives the concept of energy. So, therefore, with this physical concept we can tell mathematically that if we integrate this equation by multiplying with ds, a small displacement ds, then we arrive to the equation of energy. Again we see that this term is the term representing the force, obviously, because this term, these two terms, this is the acceleration term, temporal and convective. In total, this is dv dt. What is acceleration? It is force per unit mass, its energy is also like that. Similarly, this gives the physical concept of pressure force per unit mass, and this is the body force, that is the gravity force in this situation per unit mass, and their dimensions are like that. So, if you multiply with ds, automatically that dimensions will be the work dimension and energy dimension, and that will physically also imply the work done by the fluid element in flowing along a streamline, and that will simply give you the energy equation. Let us do that, and before doing, we take an assumption for the sake of simplicity, a steady flow. Steady flow assumptions we take. Whenever we take the steady flow assumptions, del v del t is 0. So, v is a function of s and p is a function of s. So, all parameters ceases to be functions of time. So, that we can write this equation as v dv ds in terms of the total differential. So, it becomes a ordinary differential, becomes an ordinary differential equation, dp ds plus g. So, this is the form of the Euler's equation in steady flow. Very simple, del v del t is 0, and we are removing the partial derivative notation to total derivative, because v is a function of s only, p is a function of s only. Now, what we do? We just multiply, please any problem you tell me, with ds and integrate it, minus 1 upon rho dp ds. So, it is a mathematical operation, that means we are integrating a differential equation with respect to a coordinate s, that means with respect to ds, that means we are multiplying ds and integrating it. Simple integration. What? Yes, please.
In the Euler equation, there was
Yes.
a negative sign minus g del z by del x.
No, it is plus or minus. Minus, good, very good. Minus. Very, very good. Minus. I am sorry, it is minus. It has to be minus. Okay, good. All right. Thank you. So, now we can write this as v square by 2, simple integration v dv. This is integration of minus dp by rho, very good, and this will be, g is constant. So, g z. Simply z, where z is the coordinate measured from any arbitrary datum, that is a vertical coordinate z. So, gz plus a constant. a constant C, a constant C. Now therefore, we can write this equation in this way, that we arrive to this equation, that V square by 2 plus integration of dP by rho plus Gz is equal to constant. So this is precisely the energy equation along a streamline. V square by 2 plus dP by rho plus Gz is equal to constant. If we take the fluid to be incompressible, so far we did not take any condition for incompressibility. Now if we take fluid to be incompressible, rho will come out. So V square by 2 plus P by rho plus Gz is equal to constant. So what are the assumptions for this equation? Now first of all, this equation implies the energy equation, but first of all let us find out what are the assumptions, that we did it mathematically, routine mathematical steps from the Euler's equation. So the assumptions of Euler's equations are there, that means ideal fluid, that is the fluid is inviscid. Next assumption is steady. Next assumption is incompressible for this form, not for this form. So if we refer to this form, this incompressibility will not come, incompressible. And fourth assumption is the gravity as the only body force, So these are the assumptions, that means it is, and also this equation is valid along a streamline, because we have integrated it along a streamline, which means this constant is same only along a streamline. That means now with this we can tell more briefly that V square by 2, where V is the flow velocity, that means square of flow velocity by 2 plus, if I tell it fully in words, the square of flow velocity by 2 plus the pressure by density term plus the acceleration due to gravity into some z vertical coordinate from an arbitrary datum. This summation of these three terms will be constant along a streamline for the flow of an steady ideal incompressible fluid with gravity as the only body force. We can compose in a different way. So a person who can compose nicely in English, he can compose in a much better way, but one should not forget that these are, that means steady flow of an ideal fluid, ideal and incompressible fluid with gravity as the only body force along a streamline, sum of these three terms must remain constant. So what these three terms indicate? Let us come to the physical aspect of this equation, that V square by 2 plus P by rho plus Gz is equal to constant. Along a streamline, this sum of these three terms at all points remain constant. This represents the kinetic energy per unit mass, you see. The dimension is also like this. This represents the pressure energy per unit mass, and this represents the potential energy per unit. That means the sum of these three energies are always remain same. These three energies are the forms of the mechanical energy, because mechanical energy appear in these three form only, that is the kinetic energy, pressure energy and the potential energy. So sum of these three terms can be seen as total mechanical energy. Total mechanical energy can be seen as total mechanical energy. So we can tell that the total mechanical energy comprising the kinetic energy, pressure energy and the potential energy is constant along a streamline. So therefore this equation is known as mechanical energy equation. Mechanical energy equation. The person who first deduced is known as Bernoulli, and that is why the most popular name of this equation is Bernoulli's equation. Bernoulli's equation. Now in most of the cases, the flow of fluid, Bernoulli's equation, all right. Now in most of the cases, the flow of fluid takes place, most of the cases means all practical cases, the flow of fluid is associated with viscosity. It is not an ideal flow, because no fluid in practice is having a zero viscosity. So therefore the fluid flows with viscosity. in that case the Bernoulli's equation will not be the equation of energy for a viscous fluid, because here we have considered that the flow to be ideal or fluid to be ideal or fluid to be inviscid. So, therefore, the energy equation for a viscous fluid we will have to take care of the viscous forces, that means the interaction between the shear force and the shear rate, that means the displacement, and which is more complicated. So, that first of all we will have to derive the equation of motion, then we will have to go for the equation of energy, and that is beyond the scope of your syllabus or your curriculum at this level. But one thing, we can still use the Bernoulli's equation or the energy equation for a frictional fluid or a fluid with viscosity where the frictional effects are there, with some modifications in the energy equations in solving the practical problems, that means solving the problems in practice where the fluids are real fluid having viscosity. How? Let us see now. We know that along a streamline, kinetic energy, pressure energy and potential energy is constant. That means we consider that along the streamline this is constant provided the fluid is frictionless, there is no frictional effect, fluid is incompressible, and additionally there is no extra energy added from outside or energy taken from the fluid to the outside, that means with the surroundings no interaction of energy. So, that total mechanical energy is constant. This is nothing but the conservation of energy. But if the fluid friction comes into consideration, we cannot tell always the total mechanical energy will remain constant, because a part of the mechanical energy will be degraded via friction in terms of the intermolecular energy. So, therefore, we cannot always tell this, we can tell from our common sense which we have read at school level, that total mechanical energy may not constant in a frictional system, because friction will incur certain losses, that means some part of the mechanical energy will be converted to other form of energy, intermolecular energy. So, this will not remain constant. So, therefore, if we consider the 2 points 1 and 2, we can write the Bernoulli's equation for an ideal fluid, that is basically the Bernoulli's equation. If I write this one as the first one, that is the convention for an incompressible flow. So, rho is constant V1 square by 2 plus G Z1, where Z1 is the height from an arbitrary datum for the point 1, simply we can write P2 by rho. So, if the flow is steady and ideal and incompressible, we can equate these two for 1 and 2. But what for viscous flow? In case of viscous flow, this is simply modified in this term, V square by 2 plus G Z1 is equal to P2 by rho plus V2 square by 2 plus GJ2 plus, let us write this as some GH or something here. If we write write X, where X is the term which takes care of the frictional energy that is being lost by the fluid, frictional energy that has taken care of in the curtailing the energy from the point 1 reaching to the point 2. Now, let us first see that what are these terms. So, better to understand this term, we should first write it in this form, otherwise there will be a difficulty. Mathematically, we first write this form, then only we can very well. Now, let us write, I am writing some term here afterwards. Let us write this equation in this form. What are these equations? First, implication, this is the pressure energy per unit mass, this is the kinetic energy per unit mass, and this is the potential energy per unit mass. So, this is the pressure energy per unit mass, this is the kinetic energy per unit mass, this is the potential energy per unit mass, and summation of these three are same. Now, we can express this in terms of energy per unit mole. This is more conventional way of writing this in the fluid mechanics problem. That means here we write all these terms in terms of energy per unit weight. This is energy per pressure energy per unit weight. This is kinetic energy per unit weight. This is the potential energy per unit weight in both the sides. And you know that the dimension of energy per unit weight is the linear dimension. That means in MK unit, this is meter. This is simply clear from here. Z1 is meter. V1 square by 2G is also meter. So, this term is known as head. That means head is a terminology used for fluid mechanics. This is not our head from this head as this human head is not like that. Head is the energy per unit weight. Head is the energy per unit weight. So, energy per unit weight is explained or defined as head. Okay, you can see it. Okay, energy per unit weight is the head. That is the definition of head in fluid flow. So, therefore, we can tell this is the pressure head, this is the velocity head, that means kinetic energy per unit weight, that is kinetic head or velocity head, and this is defined as the potential head. So, pressure head, this is velocity head or sometimes kinetic head, velocity head plus the potential head. Okay, potential head, this will be Z2. So, this sum of these three heads are constant. So, here x, here we write HL. What is this x? X here represents the work done per unit mass, the work done by the fluid element against friction flowing from 1 to 2, work done per unit mass of the fluid element in against friction from 1 to 2. Here it represents the work done per unit weight of the fluid element in against friction from flowing from 1 to 2. Now you see, so therefore the total energy at inlet either in terms of per weight or per mass has to be greater than this energy plus the energy which has to be considered or accountable for by moving from this point to this point. A particle or a mass has to suffer because a mass has to work against a friction. So, this is the work done against the friction per unit mass. This is the work done per unit weight against the friction. So therefore, a energy term as a loss, it is known as loss of head or loss of x, energy per unit mass. So, this is loss of it. Why it is loss? This is because we are concerning only on mechanical energies. That means this is the pressure energy, this is the velocity energy, this is the potential energy. So, we see that the sum of the pressure energy and velocity energy and potential energy what the fluid has at section 2, sum of this is less than the sum of these three. So, where it gone? A part of the mechanical energy has been lost in doing work against friction. So, it is a very important question that why we call it loss. Energy can never be lost. That means a part of this energy via friction as an agent has been converted into other form of energy, which is the intermolecular energy. If we could have taken care of the intermolecular energy, along with that we could have seen the balance is there. Since our only motto is on mechanical energy and conservation of the mechanical energy only, we will see the mechanical energy is not conserved. That means the inlet mechanical energy that any point at the upstream is more than that at the downstream by another term, which from the viewpoint of mechanical energy we call it as loss. This is a very important thing. When I teach thermodynamics, I ask that why we will call a loss of energy or loss of head. Head is nothing but energy per unit weight. This is because some part of the mechanical energy is being lost from the accountability of the mechanical energy, and that is HL. In fact, this is not a loss, this is another energy quantity which is appearing in other form rather than the mechanical energy form. So, simply writing the Bernoulli's equation, we simply add a term loss. Loss of head means this is the mechanical energy which is lost because of friction. All of you have understood this concept. So, this way we write the Bernoulli's equation for a frictionless flow from point 1 to 2 along a streamline, that I write P1 by rho plus V1 square by 2 plus GZ1, total mechanical energy at point 1 equals to the mechanical energy. Now, per unit mass basis I am writing, I can write per unit weight basis also without G, plus Z2 plus HL, where HL is known as, is very important terminology, loss of head due to friction, and usual terminology is HL, capital L or small l. HL is the, sometimes this is known as head loss. Head loss means in a viscous flow, because of the viscosity in the fluid, friction between the layers of fluids and between the fluid and the solid. So, the energy, mechanical energy which is being lost, or the part of the mechanical energy which is being used, consumed for the fluid to flow against friction. So, this is clear. So, this is known as loss. Though energy cannot be lost in fluid mechanics dealing with the Bernoulli's equation or the energy equation for mechanical energy only, we consider it as loss. This is very important to be remembered, I tell you. So, after this, well, the Bernoulli's equation, I think the implication is over. Now, I will start the analysis of finite control volumes. Analysis of finite control volumes. Analysis of finite control volumes. Now, control volumes, as you know, we have defined what is a control volume is a fixed region in space. Where the fluid crosses the control volume, it has got a fixed boundary with a fixed region. So, control volume is specified by a fixed boundary. Where the fluid may come into the control volume, fluid is going from the control volume. This is the definition of the control volume. But it is not necessary that the control volume will be static with respect to a static frame of reference. Control volume may be at absolute rest or control volume may be moving. Depending upon the choice, we can make a control volume moving with some velocities. Sometimes you will see afterwards that a unsteady flow, to make it steady for the simplification in analysis, we assume a control volume or we consider a control volume which is moving with some velocity. Again, for a moving control volume, the control volume may move with uniform velocity or with changing velocity, that means with accelerations. Now, the control volume is defined as two types. One is the stationary control volume, absolutely stationary or moving with uniform velocities. This control volume is known as inertial control volume. That means control volume without any acceleration. That means either absolute stationary or moving with uniform velocity. That is known as inertial control volume. And another type of control volume is there where the control volume is moving with acceleration. That is known as non-inertial control volume. Now, therefore, we can write inertial control volume. Inertial control volume, that is control volume we either absolutely stationary or moving with non-inertial control volume, non-inertial or moving with uniform velocity, and non-inertial the control volume which is moving with acceleration. Now, almost all practical cases we come across inertial control volume, although in some cases non-inertial control volume also comes into picture. Now, we will consider the analysis of finite control volumes, inertial and non-inertial type, through some practical problems. One of the practical problems is like this. Let us consider a pipe bend, flow through a pipe bend. Now, we will consider different practical problems where the analysis is made through inertial control volume and non-inertial. We have talked so much about control volumes. So, we have defined a Reynolds transport theorem which relates the physical laws for a system to that of a control volume, and we are so much about the definition of all physical laws through a control volume, and we have defined the equation of motion for a control volume, the equation of conservation of energy for a control volume, the equation of conservation of mass for a control volume. Now, how these theorems for control volumes are analyzed? Let us consider inertial control volume. So, through practical problems, inertial, without going from inertial control volume, a general description, we should go to a practical problem. A very important practical problem is like this. Let us consider the flow through a pipe bend like this, pipe bend like this, any general bend, diverging or a converging, a pipe bend. That means there is a pipe bend like this and the fluid is flowing. Well, the fluid is flowing in this direction. So, fluid comes, let this section is 1 1, let this outlet section is 2 2. Let fluid comes, flows through V1. Across this section we consider things to be uniform. It is a one dimensional case. Let this goes to V2. Let this angle is theta. Let us consider the pressure here is P1. Let us consider the pressure with which it goes out. Its pressure is P2. Now, I will not give any direction first. Let us consider the pressure at this section. Now, let us understand what is what happens in practice? Let us consider there is a pipe bend. So, as you know from your observation or experience that if a bend is like that, if a fluid flows through certain velocity and pressure, then goes out of this pipe bend with another velocity and pressure because of the changing cross section. So, if we make the bend free, bend will automatically move. That is a common sense. You know, when the fluid flows through a pipe, if pipe is made absolutely free, then because of the flow of the fluid, some force is being exerted by the fluid while flowing to the bend, and bend will move. You have experienced this in your common household day, that there is a hose pipe. If the water flows with high velocity in a hose pipe and it is made absolutely free, the hose pipe will go on move. So, you will have to hold it to keep it in a position. So, therefore, it is true that if the fluid flows through this pipe bend will experience some force because of which the pipe bend will move. So, we will have to give some force to the pipe bend to keep it free, some force to the pipe bend at some arbitrary direction. By our common experience, if for a bend, if the fluid flows with some velocity and pressure goes out, we will see we will have to keep a force in a particular direction with some magnitude so that the bend remains fixed. Now, physically the problem is practically prescribed like this. A practical person will be interested to know if the inlet and outlet conditions are prescribed, what should be the force in its magnitude and direction so that the bend is made stationary. Now, physically if we think how the force comes into picture, when the fluid flows through this bend, it has a change of momentum, it suffers a change of momentum. Each and individual fluid mass flowing through it suffers a change of momentum. So, where from it gets, so bend produces the change of momentum in the fluid particles while flowing through the bend. That means according to Newton's second law, the bend first, he is the culprit first who exerts force on the fluid to cause its change in momentum. So, therefore, according to Newton's third law, the fluid exerts at flowing through the bend the same force in the opposite direction to the bend. This way the bend gets a force. The same way the gun recoils. When the bullet is fired, as you know, the gun first exerts the force on the bullet to cause its change in momentum, and bullet will not leave it. According to Newton's third law, bullet will give exactly the same force in the opposite direction to the gun. So, until and unless gun is given a force in the same direction of the bullet's movement, by the amount which the bullet suffers, the gun will not be fixed, so gun will be recoiled back. So, a person who is not sufficiently strong enough will fall down. So, in the similar manner the force comes like that. So, therefore, in this case we will have to first analyze what is the force acting on the fluid flowing through this bend. So, for this reason we take first a control volume of fluid inscribing this bend like this. So, we take a fluid element at any instant out and analyze this fluid element as the control volume. Let this is the control volume of the fluid, where the velocity is V1, the pressure here is P1 acting on this control surface 1 in this direction. Similarly, the velocity is going out, this direction is theta, and the pressure is P2, and we consider in general the pipe bend is in a vertical plane. So, now we consider two axes, x in this horizontal direction, y in this vertical direction, and we consider the forces acting on these control volumes are Fx and Fy in the horizontal and vertical directions. Well, then we can find out by applying the momentum theorem the values of Fx and Fy which is being applied to this fluid volume because of its flow through the bend, and this force consists of the force because of its change in momentum plus the surface forces acting by the mutual interaction of the surface to the fluid body. So, these are summarized through the force Fx and Fy. So, if we prescribe the problem like that for a control volume of fluid, we can find out Fx and Fy now by applying the principle of momentum for the control volume in x and y direction, which I will take up in the next class because the time is up. So, today up to this. Okay, thank you.